Hey, Mr. Sams, what you got there?
Some chocolate.
Oh, man, that's not like that Russell Stover stuff.
Yeah, some loving student brought it in, and
I know.
someone who appreciates all the work we do.
Yeah, I know. Not too many of them do that, I think.
know.
Hey, so we're going to talk about energy transformations today.
Yep.
Well, I think there's some energy in there.
There most certainly is.
Probably like 600 calories in that little thing right there.
We can only hope.
So there's calories, which is energy, and we're going to talk about the transformation, not the math of it. That's later. And so what's happening is he's eating that in his face. It's going down his throat and down into his belly. And as it goes into his belly, it's changing from one type of energy to the next. And we're talking about there's actually two varieties of changes. There's exothermic, which is happening right now in his belly, and there's endothermic.
I'm exothermic.
You're exothermic. There you go. So that makes sense. Okay, let's talk about this. First of all, this is the study of thermochemistry. Now, if you think about the word thermo and chemistry, now there's things called thermal blankets, right? Mm-hmm. Or what's the thermal?
Thermal underwear, long johns.
Yeah, thermal underwear. So what's the word thermo mean?
Heat.
Heat.
Mm.
So
I
this
got
is
caramel stuck in my teeth.
yeah. So this is heat chemistry, the chemistry of heat or of energy. So we're going to study the science of energy. Briefly, there's a lot more to what we're going to talk about then.
These are all going to be in chemical reactions. There's
Yes.
other types of energy that happen.
Like when you drop a ball, physics will study that, like motion and stuff like that. So we're going to study the energies in chemical reactions. So here we have a power plant, and the power plant is producing, there's a chemical reaction taking place inside here, producing some smoke and some energy.
Yep.
Okay, and here we have something that's lit up that's also producing some energy. Okay, now let's talk about energy just in general.
Ooh, that one's not caramel.
Yeah,
I like the caramel
coconut
ones
or
the best.
something. Yeah, I like the coconut. That's one thing I do like. So here we have a guy pushing a ball up a hill. All right, now what is technically the definition of energy is the capacity to do work. Or to supply heat.
Yep.
And so this guy is pushing a ball up a hill, so he's doing work. Mm-hmm. Actually, energy isn't work. It's actually the capacity to do work. It's a little different. Okay, so energy doesn't actually have mass. This is something intriguing. A lot of people, they're not the same thing.
No.
Energy and mass, like in the universe, there's essentially two things. There's matter that has mass, like the pen here, or Mr. Sam's here, he has mass.
And I'm acquiring more mass.
He's acquiring more mass as he eats more chocolate. And energy, but energy has no mass.
Right. And we can't actually measure it directly. We can only measure it by what it does or changes in energy.
Exactly correct, yes. And so we'll actually do that in the next podcast and subsequently, Now, there are lots of different kinds of energy, Mr. Sams. But in our case, we want to talk about what's called chemical potential energy. Now, I have a picture of a Cliff Bar.
And I have a chocolate.
Yeah. Well, you see, I'm more of the Cliff Bar type. I'm going to ride my bike
raspberry.
there you go. I'm going to ride my bike on Saturday to Castle Rock from here.
I've actually started walking.
Walk?
We got a treadmill.
Mr. Sam's walks.
We got a treadmill, and I've been walking 1.5 miles every night. Thank you very
Nice. I ran 5 miles.
I don't want to hear it.
At 4:30 in the morning on my treadmill.
I don't want to hear it.
Okay, so in chemical energy, it's energy stored in the structural units of chemical substances. The what? The structural units. You know, probably should put a new word there. It's in the bonds.
Bonds, the chemical bonds.
So as you take this piece of chocolate,
there's bonds in there holding the chocolate together and holding that nice, yummy raspberry cream together. And when my body digests that, it actually breaks down those bonds, and the energy that's stored in there become other forms of energy in my body. If you've taken biology, you know that turns into ATP.
There you go.
Yeah.
Okay. So it's energy stored. It's stored in the bonds. And now, right now, as it's released as he eats it. And since this is a chemistry class, we are most interested in chemical energy. There's mechanical energy. There's solar energy. There's lots of different energies. But we in chemistry class are more interested in chemical energy.
How many calories are in these? I'm going to have to walk a little further tonight.
Yeah, Mr. Sams, I don't know. You've probably eaten way too many of those.
2 pieces.
Yeah.
160 calories, and I've already had
3
pieces.
Yeah,
I'm going to have to walk a couple extra miles.
These are about 200 calories right here.
Can of soda, about 200 calories.
Yeah, so you've had more than a can of soda here, just sitting here at this podcast.
Eating 3 chocolates, holy cow.
Yeah, that's quite a bit. Okay, so here's the idea. If you break the bonds, it releases energy, which is exactly what was happening as he's still consuming this chocolate. And the opposite is true. When you form the bonds, when you make the bonds, which typically happens actually in the plant itself as it's growing.
The chocolate plant.
The chocolate plant. There you go. Cocoa plants and sugar plants, and that's the other thing.
Yeah, they get their energy from the sun. They absorb energy from the sun, and they turn that sun energy into chemical energy in the glucose molecule.
And then you consume it.
Yeah.
And turn it right back in.
It's the circle of life.
So there is So now let's talk about energy, because there's actually the thing that's interesting is the flow of energy.
Right.
You see, energy can only flow in one direction.
Right. The cows eat the grass.
Hold on.
Okay, sorry.
So let's, before we do that, Mr. Sams, let's talk about something important. Actually, a short video clip is in order, don't you think?
Yeah, I think so.
You need in here?
Yeah, I'm freezing out here.
Yeah, that's pretty cold.
Yeah.
Hurry up, I'm sick and you're letting the cold in.
Hey, letting in cold in?
Yeah.
That's like bad
Come
science,
on.
Mr. Sam.
You're like garbage. You're letting the cold in.
I'm not letting the cold
What are
in.
you talking about? Yes, you are. I'm here, it's warm, and the cold is coming at me because it's cold outside.
That's incorrect, Mr. Sams.
Are you serious?
Yeah, I'm always serious.
So, what happens then?
Well, actually, what's happening is you're letting heat always goes from hot to cold. So actually, we're letting the hot air out, which
So-
by definition,
So, instead of me getting cold, I'm actually getting less hot.
that's correct.
So, my energy is going out to the cold air outside.
That is correct. Yes,
Oh, that's kind of weird, but I feel cold. How does that work?
because energy is leaving your body.
Oh, okay. So I have less energy, therefore I feel cold, even though I'm not getting cold. I'm
That's
getting
correct.
less hot.
That's correct.
Ah, I like it.
Hey,
Very cool.
let's go one other place to talk about this, okay?
Okay.
All right. So here I'm at my refrigerator. Now, if I open the refrigerator, of course, the purpose of the refrigerator is to make things cold. So this water bottle is what's cold because it's been in the refrigerator overnight or whatever. And why is it cold?
You mean less warm than it was when you put it in?
Right. The answer actually is that it takes the energy out of the water. So when this was warm water and it was placed in the refrigerator, the warm water then goes back here. And back here you'll find these coils. You actually can't see them, but there's little coils. And those coils are very cold. And so the energy from the warm water here goes through the air, whatever, and then hits there and gets cold. That means the energy is being moved somewhere. You have to move energy, always hot to cold. Where does it take it? Well, follow me. Where it goes is it actually goes back behind here. So if I move the refrigerator out, you can't see it, but this area is all kind of warm. And actually down here even, yeah, you can feel that, Mr. Sams. It's warm, isn't it? And so it's warm. And so if you feel the back of your refrigerator, you'll discover that it's warm because it's moving the energy from the refrigerator to the back of the refrigerator. So an
Out
interesting
into the room then.
out into the room. So an interesting thing. Let's say it's a really hot summer day, and you're hot, and so you say, well, I want to cool off.
Well, yeah,
my
I'm
room.
going to go open the
I
fridge
should
and I'm
just
going to
open
stand
the
right in
fridge.
front of the freezer and look at all of Mr. Winstead's
Weird enchilada things.
enchilada meals.
Yeah, but the
But,
problem.
it's nice and cool if
It
I'm
is,
hot.
it is cool, Mr. Sam, but you know the problem?
That can't cool my room, right?
It actually will heat up your room. Because what you're going to do is the warm air from the room is now warming up the freezer.
Oh, the coil's in the back again.
And then the coils in the back is going to then take it back in.
And they're going to dump it out the back of the fridge again
So you're
and
not doing
warm
anything.
the room.
And since it's not a perfect system, it does not a perfectly efficient system, it will actually heat up your house in the long run. Now, in a few short seconds, it will cool you down, but it will actually heat up your house. So, okay. We just learned that energy can only go from hot to cold.
Yeah.
The reverse cannot happen, okay? So, now let's talk about this thing called the system. The system is the part of the universe that you want to study. Okay, so when you are doing the experiment, we were trying to study, well, which system when we were going outside and stuff?
The system probably would be the room.
The room.
Yeah.
And so from
Or
the
me.
perspective, or you, yeah. So
Yeah.
the system was the room, or Mr. Sam's, and that's the part we wanted to study.
Right.
Okay. Usually in in chemistry class, we're interested in the chemical reaction.
Right, and you as a scientist get to define the system. When you
Yes.
are doing something, you say, okay, this is the system that I'm studying, you define the parameters, and then you run your experiment within those
Frankly,
parameters.
different types of chemists study it differently. Or different types of scientists, I should say. Chemists typically think of the reaction as the system, and physicists usually think of what we would call the surroundings to be their system. It sort of depends on your perspective.
Yep.
Not that critical that you understand that distinction. All right. Now, the surroundings is, well, everything else.
You define the system, everything else is surroundings.
So if we were to think of this particular beaker where a reaction would take place,
That's
if it was
a
an
flask.
acid, a flask, I said a beaker?
You did.
And I added something to this, some chemical, maybe a piece of magnesium or something like that, then this would be the system, and the surroundings would be everything outside it. This would heat up possibly or cool down, so the surroundings are the things on the outside.
Yep, and together, the system plus the surroundings equals the universe.
Yep, there you go. All right. Now, there's a thing called the law of conservation energy, named by Hermann Helmholtz. Okay, and he said that energy can't be created or destroyed, just transformed. What does that mean?
Well, that means we can change it from one form or another, but we can't make it or get rid of it.
So, for example, Mr. Sams just ate the chocolate.
Yep.
And so it was chemical potential
chemical.
energy. And now it has been converted into most likely heat energy, or it's being converted into heat energy to heat his body.
If it doesn't, then it's going to go back into chemical energy, and it's going to get stored as fat.
That is correct.
As chemical energy in my body, which is why I need to go walk an extra mile and a half tonight on the treadmill.
There you go. All right, so let's talk about exothermic. So there's two ways that energy can be transferred. Either exothermically, and exothermically is when the energy is released to the surroundings.
Yes.
This is a classic picture right here. We have a crazy scientist.
It looks kind of like Woody Allen.
He does kind of, doesn't he?
Yeah.
So
Looks like my Facebook profile picture, too. Have you seen that?
yeah, I have,
With
yeah.
my
yeah.
big fire. Yeah.
And so what we've got is we've got a fire, and the energy, this would be the system right here. And the energy is being released. Everyone's standing back because it's quite hot. Some kind of a big fire experiment.
Yep.
And these are the surroundings. So it's going from the system outward, and that is called exothermic, when energy is released to the surroundings.
Right.
Okay, I think we should actually do our own exothermic chemical reaction.
I think so, too. These are a lot of fun.
Yeah.
Today we'll be doing an experiment in which we make a flash powder from silver nitrate and powdered magnesium. This is a highly water-sensitive compound that'll give a nice, really bright flash and a quick explosion when you drop water upon it. So, we've got our first small little bit of magnesium powder right here, which will be grinded up, well, not grinded up, which will be mixed with our silver nitrate. We've used very small amounts of both, as you can see. As you can see, this paper towel here is what we'll be using to mix them, since we want a very low friction environment in which the chemicals can slowly roll over each other to create a compounded mixture. We don't want to induce a lot of friction, and we just kind of want to let them settle out as they see fit so we get a nice even mix without stressing it much. So I'm going to go ahead and pour the magnesium and the silver nitrate in the center here, and then slowly fold the paper towel both directions in a manner called diapering, so that the chemicals slowly roll over each other and create our mix. Here we go. So now that the chemicals have been diapered together to be mixed some, I've placed them in this little aluminum foil containing thing. As you can see here, they're sitting there in the middle, so we'll take this outside so that we're safe as possible with this, and put a drop of water on it and see what happens. We are now going to test this reaction. So in this particular reaction, when the water hits the silver becomes molten and catches fire. As you can see, it flashed extremely brightly. This is an extremely unstable reaction, so never try this unless you are properly supervised.
Way cool. All right.
Okay,
That was amazing, Mr. Sams.
Yeah.
All right. So, hey, but the opposite is endothermic. These aren't usually as exciting, but they are still part of the universe.
This is pretty cool.
This one will be cool. We'll show you. So this is when energy is absorbed into the system. So here we have a system where the surroundings are warm. Because remember, things always go from hot to cold.
Right.
And this would be cold. And so the energy is going to go into the system from the outside.
Yep.
And so this would be endothermic. Energy goes into the system or is absorbed into the system.
Yeah.
Make sense? All right. So I think we should do a video clip.
Today we'll be talking about endothermic and exothermic reactions. What we have set up right here, first of all, is an endothermic reaction, which means it draws heat in from the surroundings into the system so that the reaction actually gets warmer and the surrounding area gets cooler. In this case, we'll be working with barium hydroxide, BaOH2, and ammonium thiocyanate, which is NH4SCN. So for this particular experiment, I'm going to take a drop of water here, extract it, place it on this block of wood, bam, place this beaker on top of it, and cause a reaction between the two. Since this is endothermic, it will be drawing heat out of the surroundings, in this case the water, which will cause the water to freeze, and we'll be able to pick up the block of the wood with the beaker.
Go.
So now I'll be adding the barium hydroxide first, right into the beaker over our water.
Wow, that was pleasant.
Bam. Followed by the ammonium thiocyanate. I'll go ahead and stir these two together. They'll get kind of goopy and start drawing in heat from the surroundings into the system. Endothermic reaction. As you can see, the reaction has occurred now, and we've got a nice combination of the two. The reaction has probably a little bit of time left, but for the most part it's completely reacted. You can see here the water here is quite chilly, and the stuff directly below the beaker is frozen. Very good. Now that it's frozen, bam. Woo!
And no, take it apart and show them that there's nothing in between.
Yeah, to reveal that I'm totally legit.
Woo!
So this too. All right. That was cool too.
Also very cool.
Very cool.
It was cool.
Cool. Yeah.
Dumb.
Yeah, all right.
All right.
All right, now we should talk about the difference between heat and temperature.
Okay.
A lot of people get these confused. Okay,
right.
so here's the question: which is warmer? Not warmer.
Warmer.
Which has more energy?
Okay.
Actually, before we do that, let's do this.
Okay.
Heat is all of the energy of a system.
Okay.
So heat is all of the energy. So if I have a big lake right here.
Okay. Looks like Rampart Reservoir.
Yeah, it does. I think it is. It is, in fact. Right. Yes, it is. Or I have a small cup of coffee. Which has more heat?
Total heat?
Yeah.
Total heat is going to be the lake.
You know, I think we should probably take a field trip right now.
Let's do it.
So let's take a field trip to a triathlon. And so we'll go to the triathlon and talk about this, okay?
Can I walk on my treadmill at the triathlon?
Sure, but they'll think. So, hey, now we learned about some more stuff about triathlons.
Yeah.
And we saw that, of course, there's more energy in the
lake.
The lake than there is in the coffee cup.
Mm-hmm. Even though the coffee cup is hotter in terms of temperature.
Because there's a difference in temperature, all right? Okay. So let's just kind of summarize the difference between heat and temperature.
All
Let's
right.
list heat and temperature.
All right,
Table.
heat is our total energy.
This is total energy.
And temperature is an average of the kinetic energy of the molecules.
So average kinetic energy. Remember, we talked possibly, we did, on a previous podcast about the Boltzmann diagram, and the average kinetic energy is this amount. So some chemicals or some molecules would have high energy, maybe up here, and some would have low. This is the average one, where this is the total. So if you think of this graphically, the total energy in this graph is essentially everything under the curve. The average is only just the average molecule right here.
Yeah.
So we can think of it graphically, okay? So how does that play out in a chemical reaction or in a chemical equation? Okay, so if it's exothermic, here's what the energy is going to go on the right side of the equation.
Right. So, and it's the right side because if energy is going out, it's like a product. It's being released from the equation.
So here's a classic reaction: methane plus oxygen. The exothermic reaction that we saw earlier in our podcast.
Yep.
6CH4 plus O2, and that released energy. So if it released energy, we would put energy right here.
Right. Exothermic, it goes on the right
It goes
side.
on the right
it's being
side.
released as
Now,
a product.
as a side note, that typically, not just typically, is actually a number. So this might be like 212 kilojoules. I don't know the exact number. We will learn later how to calculate that number. So I'll write the word energy, but note that it's actually a particular number. Okay. And, I'm really good. It's actually, all right, it's not 212. It's 900, no, I can't write, 902 kilojoules. Now, Mr. Sams, there's a negative sign
Yes,
there.
there is.
What does that mean? I
Negatives-
didn't know you could have negative energy.
Negative energy means it's going away from the system. The system is losing its energy.
Yeah.
Means it's exothermic, so we put a negative sign when we talk in terms of delta H.
So, here is the actual equation right here.
Right. Notice when you write it in the equation, the negative sign isn't there. The fact that you're putting it on the product side implies that it's exothermic.
Yep.
And so when you write it in the equation, you don't put the sign. But if you're just talking about the value of delta H, you do put the sign.
That's exactly right. Okay, good. And actually, here's a graph. Make sure you graph this. This is the exothermic energy graph.
Right. Notice the energy of your reactants are greater than the energy of your products.
So it'd be CH4 plus 2O2 makes CO2 plus 2H2O. This is the reaction we had just a
Right.
little bit ago. And this, they call delta E. We actually don't usually call it delta
No.
E. We call it delta H.
That's the
This is
change
the
in
difference
energy.
from here to here. It's the change in energy as it went down. And this number, if you were to measure it on the graph, would be 902 kilojoules. So it goes down 902 kilojoules.
Right.
Make sense? All right. All right, now let's talk about this in an endothermic reaction. So in an endothermic reaction, the energy goes on, well, the opposite
left
side,
side.
not the right side, but on the left side. So here's a classic reaction that is
All right.
endothermic reaction. Okay? Now this we didn't do this one, and here is the value of delta H. Notice that it's positive.
Okay.
And so if it's positive, then you put it on the left
The
side.
left side. Positive delta H means that it's going into the system. The system is gaining that much energy.
Yes, and so energy, we could also just write the word energy on this side, but it's actually a number, and I want you to understand that. In this case, it's 76.7. Actually, we'd say just 76.7 kilojoules, not per mole, but kilojoules, wouldn't we, Mr. Sams?
Probably, yeah.
Okay. All right, so here is an endothermic reaction. I would label that endothermic reaction graph.
Yeah, notice that the energy of the reactants is lower than the energy of the products, meaning we have to put energy into the system to get the reaction to proceed.
So this would be, I think it was a 3 here and a 2,
No.
a 3 on a 1,
and a
and this
2.
was a 2.
Yep.
And the difference here, the A right here,
No,
this
not A.
would be,
C.
pardon me, C, thank you. C would be 76, I think.
70, whatever it was.
Whatever it was, we'll go back. I think it was 76.
76.7.
76, we'll call it 77. 77 kilojoules. It rose up 77 kilojoules. Later on, we might talk about this thing, the activated complex, and how that works. But that's going to be like unit 10.
Yep, later on.
So let's not worry about it. Really notice there's a difference in the energies. Okay? So that explains what exothermic, endothermic. We had lots of cool demos. We got a trip to the triathlon.
Yeah.
Yeah, and
And a
outside.
trip up. No, that was the last time.
Yeah. Okay.
Yeah.
Well, so